So just as the first derivative tells us when a function is increasing, we can use the second derivative to give us information about concavity. So when the second derivative is positive, the graph will be concave up, and when it's negative, the graph will be concave down. Another way of saying this is that we can use the second derivative to get information about concavity. So let's do an example on the next slide. So let's use the concavity test to determine the intervals on which the graph is concave up and concave down. So we've got a degree 4 polynomial here. We're going to want to find its second derivative to get at information about concavity. So first we'll find the first derivative, which is going to be negative 4x cubed plus 12x squared minus 4. And then we find the second derivative to get negative 12x squared plus 24x. And that factors, so I'm going to take out a negative 12x and get x minus 2. And so now what we want to do is set this second derivative equal to 0. Now, what we're doing when we do that is we're finding inflection points, or the potential areas where there could be inflection points. Inflection points, remember, could happen where the second derivative is undefined, but that's not going to happen in this case because this is just a degree 2 polynomial which is defined everywhere. So we really just got to set it equal to 0. So negative 12x times x minus 2, that means that x equals 0 and x equals 2. So now what I do is you'll make a number line just like you did with the first derivative. So we'll make an f double prime number line, or I guess a y double prime number line in this case. We're going to put 0 and 2 on that number line, and then we're going to plug values in in the values in between 0 and 2, and then to the right of 2 and to the left of 0 to get information about concavity. So I'm going to let's plug in 1 into the derivative. I'm going to use this version here. So that's negative 12 times 1 minus 2. And I get negative 12 times negative 1, which is a positive. So that's a plus. If I plug in the derivative, if I plug in 3 to the second derivative, I get negative 12 times 3 minus 2. And that ends up being a negative. So I think that's negative 36. But we don't really care. We just care whether it's positive or negative. And then we plug in, let's say, negative 1. And when you do that, you get negative 12 times negative 1 minus 2. And that is 3 negatives, you get a positive. So you get a positive. Nope. 3 negatives gives you a negative. So that's a negative. All right, and so now we're going to answer this question. Where's the graph concave up and concave down? This graph is concave up, where the second derivative is positive, so on the interval 0 to 2, and concave down on the intervals where the second derivative is negative, so that would be negative infinity to 0, union 2 to infinity. Now I noticed something odd about the book I used, which was that they didn't use hard brackets when doing concavity. So for instance, the 0 and the 2, they just put soft brackets. I'm not sure why they did that, because we noted that you use hard brackets when you're talking about where a function is increasing or decreasing based on its based on the first derivative, right? You still include those endpoints, and I did a video on that. And since the definition of concavity is it's where the first derivative is increasing or decreasing, you would think you would put those hard brackets on. So I'm putting them on, but I think, I mean, I'm not sure why the book didn't do that. It's kind of a strange idea, but in any case, I think if you come across test questions, I think they kind of dodge that issue anyway. But I'm using hard brackets by definition of increasing and decreasing. We're going to finish up this section on the second derivative by looking at a function that's probably more difficult than the ones we've seen so far. And we're going to look for just inflection points. So let's just remind ourselves that inflection points can occur when the second derivative equals 0 or when the second derivative is undefined. A lot of people forget to check the second case, but they can occur when the second derivative is undefined. You could get a vertical tangent, in a graph like this. That would be an inflection point. So just keep that in mind. So let's deal with the business of getting the second derivative of this thing. I recommend maybe distributing that x to the 1/2 so that we don't have to use the product rule. And by doing that, you'll want to think of x to the 1 as x to the 2/2. And I think by doing this, you're going to see that it'll end up making getting to the second derivative a little easier. So x to the 1/2 times x to the 2/2, we add exponents when we're multiplying with the same base. So that's x to the 3/2 plus 3x to the 1/2. So now we'll take the first derivative just using the power rule. Subtract 1 from 3/2, you get 1/2, plus 3/2 x to the negative 1/2. And now we got to take the derivative of the derivative, so this ends up being 3/4. Subtract 1 from the exponent, x to the negative 1/2, minus 3/4 x to the negative 3/2. So it's kind of a crazy looking function. Let's write it in a better way. This is going to be 3 over 4 square root of x minus 3 over 4 times, let's just write it as x to the 3/2. So the first thing I would notice is that we have, at x equals 0, I'm going to make a number line, or get my number line started over here. First thing to notice is that this is the second derivative, and it's undefined at 0, because you can't plug in 0 into this. You'll be dividing by 0. So that needs to go in our number line. That's a candidate for an inflection point. However, it's instantly no longer a candidate because of the square root under there, this function is not defined to the left of 0. You can't plug in negative numbers into the second derivative. And in fact, if you go back to the original function, you can't plug negative numbers into that as well. So the domain of this function does not even include negatives. So I'm just going to erase that. And now we're only dealing with a function that begins at 0. All right, so again, that's a second derivative number line. All right, so we've got some information about this graph. The other candidate for an inflection point is where it's equal to, the second derivative is equal to 0. So we're going to set this equal to 0 and solve. So what I might recommend is adding this term here to both sides so that we get 3 over 4x to the 3/2 equals 3 over 4 square root of x. And then what I might do is, quote, cross multiply. So if you do that, you get 12 root x equals 12x to the 3/2. And you can get rid of that square root of x and that fractional exponent by squaring both sides. So this ends up being 144x equals 144x cubed. So you can divide off those 144s, and now you just get x equals x cubed. So let's finish the algebra up here. I've got x equals x cubed, so we'll subtract x from both sides and factor. So now I have 0 equals x times x plus 1, x minus 1. So notice 0 showed up again as a candidate, but we already know that that's not going to be an inflection point, because to be an inflection point, the concavity would have to change, and it can't change at an endpoint, right? There's only one side to that value. So that's already on our number line, but it's an endpoint. This implies that x equals -1, but that's not in the domain, so we can ignore that guy. And then the last one, x equals 1, is actually what we need to put on our number line as well. So we'll put a 1 here. Alright, so we're almost there. We just have to analyze the second derivative on the interval 0 to 1 and 1 to infinity. So let's plug in a value to the right of 1 first into the second derivative. So here's where you want to make your life easy, because the second derivative is kind of a crazy looking function. So you're taking square roots, right? If you look at the second derivative of this version. So let's plug in 9. So y double prime of 9 equals 3 over 4 square root of 9 minus 3 over 4 times 9 to the 3/2, which equals 3 over 4 times 3, which is a fourth, minus 3 over, so 9 to the 3/2 is the square root of 9, which is 3, cubed. So that's 27. So this is 3 over 4 times 27. And that is a smaller fraction than 1/4. So that means that this is going to be positive. So see that reasoning there? I didn't really actually evaluate this. You can if it makes you feel more comfortable, but we only care if it's what the sign is, not the actual value. So I got to put a plus there. Now, here's where we have to be kind of clever. Between 0 and 1, there are no whole numbers, and that makes a lot of kids uncomfortable. But that's okay. We can still plug in something that's pretty reasonable and get and analyze the second derivative that way. Let's plug in something that has a square root, but that maybe is a fraction. So how about like a ninth? Let's do y double prime of 1/9. So that's going to be 3 over 4 times the square root of 1/9 minus 3 over 4 times 1/9 to the 3/2. So you can see why having some good knowledge of exponential properties is going to be useful for these problems. But 3 over 4 times the square root of a ninth is a third, minus 3 over the square root of a ninth is a third, cubed gives me 1 over 27. So this ends up being 3 divided by 4/3 minus 3 over 4/27, which equals, divided by a fraction multiplied by the reciprocal, 9/4 minus 27 times 3 is 81/4, which we can see is going to be negative. So that's all we care about, it's negative. So we put a negative there, and now we can find our inflection point, because just zooming in on this again, our inflection point is going to be where the concavity changes. So the concavity changed there, and where you can draw a tangent line. So how do we know we can draw a tangent line at 1? Because we know that because if you plug 1 into the first derivative, over here, you get out a number, right? You're not dividing by 0, you're not taking the square root of a negative. That means that you can draw a tangent line. So this is an inflection point, because the concavity changed and a tangent line could be drawn in this case because the first derivative exists. That means you could draw a tangent line. So we have an inflection point. And I'm just going to give the x value at x equals 1. If it asks for the actual x and y values, or if you interpreted this problem to mean that, you would just have to plug 1 in. So I guess I'll do that. So y of 1 equals the square root of 1 times 1 plus 3. So that's 1 times 4, which is 4. So let's just say at 1 comma 4 to get the actual point. But often you're asked just to find where it occurs. So that was kind of a crazy function. There's a lot of technical issues to work through. So, but these show up a lot of times on AP exams. So if nothing else, it'll convince you to try to get fluent with these exponential properties that you've learned probably in your algebra classes, but maybe aren't so good with. So anyway, you just want to study some of the mechanics of this problem in order to be successful on future problems.